All right, so we're calling this one Getting Ready 15 and a half because I combined two assignments, the Getting Ready 15 and Getting Ready 16. So we're going to look at arithmetic and geometric sequences together rather than separately. So how are arithmetic and geometric sequences similar? So how are they alike? I would say that the main thing that you would need to identify as part of your answer here is that once the pattern is established, it doesn't change. We call the pattern of change in an arithmetic sequence a common difference, meaning we are adding, or technically it could be subtracting, but adding a positive or negative number constantly, over and over and over the same number. It cannot change once the pattern's established. In a geometric sequence, we call it a common ratio, but it's really what we mean is it's a multiplier, and that multiplier cannot change. If you're going to multiply by 2/3, you need to do that for the entire sequence. So I guess the main thing to identify, the main similarity would be that the pattern does not change once established. Okay, now how are they different? That's a big, easy one to identify. Arithmetic sequence has to be adding. Even if it looks like subtraction, that's adding a negative. And geometric is defined as multiplying. Even if it looks like it is division, it's actually multiplying by a fraction or decimal between 0 and 1. Okay, so we're going to determine if the sequence is arithmetic, geometric, or neither, and then determine both types of equations for the pattern. I guess the second part is, the first part is to tell what kind. The second part, we're only going to do that if we have identified it as arithmetic or geometric. If we say neither, we're done. Okay. So number 3, I see add 4, add 4, add 4. So this one is an arithmetic sequence. We need both our recursive and our explicit equations. Okay? So recursive, remember it's a two-parter. We have to identify something to start with. So f of 1 here is 5. And then each successive term is found by taking your previous term, f of x minus 1, and adding 4. For your explicit equation, being that it's arithmetic, it needs to look like y equals mx plus b, slope-intercept form. So we're going to say f of x is equal to our constant rate of change, 4, times x. Now the plus b, our b stands for our 0th term. Well, we don't have that in this sequence, but we can extend our pattern in reverse. If this is the first term and the second and the third, the 0th is 1 before the 5. Well, if we had been adding 4, we would have to subtract 4 and say our 0th term would have been 1. So f of x is 4x plus 1. All right, number 4, this goes down 30, down another 30, down another 30. So it's adding negative 30 or subtracting 30. That makes this one also arithmetic. We know we'll need the 0th term, so let's go ahead and jump backwards one place. Rather than subtracting 30, if we're going in reverse, we add 30 and say our 0th term is 90. So, recursive and explicit equations. Recursive, we would start with our f of 1 is 60, and then we would say f of x is formed by doing f of x minus 1 minus 30. Our explicit formula, again, which needs to be slope-intercept form, f of x is equal to minus 30x, or negative 30x, plus 90. Number 5. Number 5, if we try to look to see arithmetic, it looks like it goes down 30, but the next one doesn't. It would only go down 15. So could it be geometric? What would you multiply 60 by to make it 30? Well, that's half. 30 is half of 60. 15 is half of 30. Half of the 15 is 15 halves. So this one is geometric because it is multiplying by 1/2. So our recursive equation would be f of 1 is 60, and then our f of x is half times the previous term, f of x minus 1. And you can put that times 1/2 either in front of the f of x minus 1 or behind it. It's up to you. Our explicit equation, we would need, again, the 0th term. So if this is first, second, third, and fourth, to go back to the 0th, we need to reverse our pattern. And rather than multiply by 1/2, we ask ourselves, what is 60 divided by 1/2? Or what number, if we chop it in half, is equal to 60? And the answer to that is 120. Okay? So our explicit equation for geometric must look like y equals a times b to the x. So we say f of x is equal to the 0th term, the 120, times the b is our multiplier, our common ratio, 1/2, and then to the x power. And number 6. I see from 4 to 7 goes up 3, from 7 to 10 is up 3, 10 to 13 is up 3. So we're looking at arithmetic again. We'll make our recursive and explicit equations. For recursive, our first term is 4. Each new term will be the last term plus 3 more. For our explicit formula, we'll need the 0th term. So if we go backwards in our pattern from 4, subtract 3, we're back at 1. So f of x is equal to the constant rate of change, 3, times x, plus the 0th term, 1. All right, still looking at sequences, but a little change in directions here. So first, we're going to find the first 5 terms. We'll do that as if it were an arithmetic sequence, and then do it as if it were a geometric sequence. Same starting value and same rate of change, just difference being, is that rate of change a common difference or a common ratio? And then we'll try to explain which one we think would get us quicker or get us a larger value for f of 100, and why is that? Okay. So, arithmetic sequence, we start at 2, common difference is 3. So f of 1 is 2. To get f of 2, we add that common difference of 3, so we have 5. Add another 3 is 8. Add another 3 is 11. Add another 3 is 14. For geometric, f of 1 is 2 again, but now common ratio of 3 means we're going to multiply by 3. So 2 times 3 will give us 6, times 3 is 18, times 3 is 54, times 3 is 162. So we can see that the geometric sequence very quickly outpaced the arithmetic. So whose value do you think will be more for f of 100? I hope it's obvious to you that the geometric sequence would. And the reason it's going to get there or become such a high number quicker is because multiplying by 3 grows much, much faster than adding 3. Now that would be true no matter what the common ratio was, as long as it was above 1. Okay? It's exponential compared to a linear function. All right, so if we take another arithmetic sequence, this time our common difference will be 10. And we're going to keep the same exact geometric sequence we had above. So f of 1 is 2 and our common ratio of 3. So we can go ahead and fill that one in, just copying from number 7. So what if we take an arithmetic sequence, and this time our rate of change is actually a much larger number than it was with the geometric. Okay? So we're going to add 10 to our first value. That gives us 12. Add another 10 is 22. Add another 10 is 32. Add another 10, 42. Well, now the arithmetic sequence stayed larger a little longer. Up here, by f of 2, our geometric sequence was already a larger number, and it never relinquished that. But down here, number 8, the arithmetic stays larger at f of 2, at f of 3, but by f of 4, our exponential function, our geometric sequence, has surpassed it, and it will never give that up. So, once again, we're going to have our geometric sequence have a much larger number at f of 100, and it's because it's already larger by f of 4, then continues to grow exponentially. All right, number 9. Okay, now we're going to do this. It's a little newer to us. Arithmetic and geometric means, okay, which is we're given part of an arithmetic or geometric sequence, and we have to figure out one or more missing values within the sequence. Not at the end, not to continue it, but somewhere inside it. Okay. So what we know when we're told that this is an arithmetic sequence, and there's nothing specific about the table that should say that to us, just the directions tell us it's arithmetic. That means it adds something to get from one term to the next. So I'm going to say from 3 to this missing term added something called m. That same value was added again to get to 12. So make sure we're showing our work here, and this is the method that I showed you in class. You're going to start at 3, you add m twice. Now we could write that as plus m and plus m, or we could write it as 3 plus 2m, and then we end up at 12. So whether you start your work at this step or one step ahead of there where you've already said I'm adding m twice, either of those is acceptable. But now we just have a little linear equation to solve. If we subtract 3 from both sides, so that 2m is 9, that means dividing by 2 on both sides, m is 9/2 or 4.5. Okay, so if the common difference, that's what we just found here, we just found our common difference, our constant rate of change, if that's 4.5, then this term in between here, 3 plus 4.5 must be 7.5. And then if I had added 4.5 to that, I'm at 12. Okay, number 10. Again, we only know it's arithmetic because of the directions. Okay, nothing about the table says arithmetic. So we're starting at -2. We're going to add, because it's arithmetic, we're going to add m once, twice, 3 times. Yes, there are only 2 missing values, but that m value, that common difference, must have been added 3 times to get from -2 to 26. So I'm going to add 3m and end at 26. So solving this little linear equation, if I add 2 to both sides, I get 3m equals 28. Divide both sides by 3. So m is, now I prefer the value 28/3. It cannot be simplified. If that's hard for you to work with, 3 goes into 28 9 times, which is 27, leaving a remainder of 1. So you could call that 9 1/3. Okay. So let's test and see how that works. -2 plus 9 1/3 is 7 1/3. Add another 9 1/3, we're up to 16 2/3. Add another 9 1/3, and we get to 26. Okay. Whatever you do, though, do not round that to 9.3. 9.3 is not the same as 9 1/3. Okay, Now, in number 11 here, there's a couple extra boxes after the 6, and we will fill those in, but they don't really come into play as we're trying to find our common difference and our arithmetic mean in between the 24 and the 6. So we've added m twice. It only took 2 adds to get from 24 to 6. We don't really care what happened after that until later. So start with 24, add m twice, and result is 6. Solving this little equation, subtract 24 on both sides. So 2m is equal to negative 18. Divide both sides by 2. M is negative 9. So our common difference is negative 9. 24 minus 9 is 15. 15 minus 9 is 6. 6 minus 9 is negative 3. Negative 3 minus 9 is negative 12. Number 12. This time, to get from 16 to 2, we're going to have to add our common difference once, twice, 3 times. So 16 plus 3m equals 2. Subtract 16 on both sides. So 3m is negative 14. Divide by 3. M is equal to negative 14 thirds. Now again, that does not divide nicely. It's a repeating decimal. You do not want to use that. You either keep negative 14 thirds or negative 4 and 2 thirds if you want to put it as a mixed number. So 16 minus 4 and 2 thirds would be 11 and 1 third. Minus 4 and 2 thirds would be, let's see, minus 4 is 7 and a third, and then take away the 2 thirds is 6 and 2 thirds. And then subtract 4 and 2 thirds, you're down to 2. One more time to get to our 5th term in the sequence would bring us to negative 2 and 2 thirds. Number 13. Now we are switching to geometric means, okay? So we can look even at the same exact tables, but say we want them to be geometric sequences, and our answers are all going to be different now. Our method is different, which again, we need to show that method. Our method is going to be different, our answers are going to be different. Okay? So in a geometric sequence, we multiply. That means I multiplied 3 times some value, I'm going to call it r, to get this second term, the one that's missing. And then I multiplied that by the same value r to get to 12. So the way I would set this equation up is I'm starting at 3, I'm multiplying by r, then multiplying by r again, and I end up at 12. Well, we all know that r times r is actually r squared. So you'll probably start your work at this step rather than the one above there. So 3r squared must equal 12. Let's see, to solve that, we'll divide both sides by 3. So r squared equals 4. And we need to take the square root of both sides. Now remember, when you do that, when you take the square root of both sides of an equation, there are always 2 answers. So r is positive and negative 2. What this means is there are 2 possibilities for the r value. Okay, let's try positive 2. If we use positive 2, 3 times 2 is 6. 6 times 2 is 12. It worked. But if we had used negative 2 instead, 3 times negative 2 is negative 6. Multiply that by negative 2 is 12 again. So either of those answers, 6 or negative 6, are acceptable. Number 14. Again, we're working on geometric, so 2 multiplied by, since it's geometric, we're multiplying by this r value once, twice, 3 times here. Times r, times r, times r to go from 2 to 54. So 2 times r to the third is equal to 54. Divide both sides by 2. R to the third is 27. And now we would take the cube root of both sides. The cube root of r to the third is r. The cube root of 27 is 3. Now, cube roots only give us one value, not two. We don't get both a positive and a negative. You get either positive or negative. Okay? The difference is this was an odd power. So if r is 3, 2 times 3 is 6. 6 times 3 is 18. And then 18 times 3 gives us our 54. Number 15, again, there's a couple empty boxes after the 20. Not concerned about that right now. We are going to multiply by our common ratio once, twice. So 5 times r to the second, since we used it twice, equals 20. Divide both sides by 5. So r squared equals 4. So once again, that's the exact equation we had 2 problems ago. We have to take the square root of both sides and expect 2 answers. R is both 2 and negative 2. So let's do this 2 possible ways. If we use the positive 2, we'll split our boxes to have 2 answers each one. So 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. Had we decided instead to use negative 2, 5 times negative 2 is negative 10. Multiply that by negative 2 is 20. Times negative 2 is negative 40. Times negative 2 is 80. So every other value changes if you decide to use the negative one. Okay, number 16. Again, geometric. This time you have your common ratio used once, twice, 3 times, and 4 times. So this would be 4 times r to the 4th power is equal to 324. All right, divide both sides by 4. So r to the 4th gives us 81. And just like to the inverse of r squared was the square root. The inverse of r to the 3rd was cube root. The inverse of r to the 4th is take the 4th root of each side. So the 4th root of r to the 4th is r. Now, do we expect 1 answer or 2 answers here? Well, there are 2 different values, both a positive one and a negative, that if multiplied by itself 4 times give us 81, and that is 3. Right, because 3 times 3 times 3 times 3 is 81. But also negative 3 times negative 3, which would be 9, times another negative 3 times another negative 3, which is another 9, also gives us 81. So again, we expect 2 answers, and it's because the exponent here, or the exponent here even, was an even exponent. Whenever you have an even exponent in the equation you're solving, you should expect 2 answers. Right, so let's split our boxes up, go through this twice. If we use positive 3, 4 times 3 is 12, 12 times 3 is 36, 36 times 3 is 108, and 108 times 3 gives us our 324. If we use the negative 3, 4 times negative 3 is negative 12, times negative 3 is 36, times negative 3, negative 108, times negative 3 is 324. All right, and for these last couple, we are going to try to turn whatever information we're given into an explicit equation. And we're told they're all geometric, so that means I can narrow down what I'm looking into. I want my equations to all look y equals a times b to the x, where a is my y-intercept, or 0th term, and b is my common ratio, or my multiplier. All right, so if f of 1 is 8 and the common ratio is 2, that means the sequence looks like 8 multiplied by 2, 16, multiplied by 2, 32, 64, and so on. Well, to make an explicit equation, I'm going to need one more piece of information. This is the 1st term, 2nd term, 3rd, and 4th. I need the 0th. So if rather than multiplying by 2, I divide that 8 by 2, it means the 0th term would be 4. So my function is f of x equals 0th term 4 times multiplier 2 to the x power. Okay? Now we're given the recursive formula, and we want to turn that into explicit. So let's think about this. F of 1 is 4, means my first one is 4, and this is telling me that I multiply by 3 to get the next term. So times 3 is 12, 12 times 3 is 36, times 3 is 108, and so forth. Again, for explicit, I'm going to need to go backwards one place. So if this is first, second, third, and fourth, my 0th term would be 4 divided by 3. Well, that's simply 4/3. So f of x is equal to 0th term times the common ratio to the x power. Number 19. Once again, we have recursive given to us. So the first value is 5/3. The common ratio is 4. So 5/3 times 4 would be 20/3, times 4 would be 80/3, and so on. We're going to need to go backwards one place to the 0th. So rather than multiplying by 4, we need to do 5/3 divided by 4. So 5/3 divided by 4. Again, that's 4 over 1. And to divide fractions, you multiply by the reciprocal. So 5/3 times 1/4 is 5 over 12. And that does not simplify. Please do not make it a decimal. The decimal that you would round to is not the same thing. So the 0th term is 5/12. Function then, f of, I guess I can use n since that's in the problem, f of n equals 0th term times common ratio. Now if you switch to an n to match the equation in number 19, then you also have to switch this and make it to the n power. I'm not concerned with whether you used n or x, as long as you are consistent throughout your equation. You can't mix and match.